chemistry students. These are your notes for topic 8.4, acid-base reactions and buffers. We're working towards the same enduring understanding that we did before, but in this lesson, our objective is to explain the relationship among the concentrations of major species in a mixture of weak and strong acids and bases. So when we have a strong acid and a strong base, they perform a neutralization reaction. So this is an example of a neutralization reaction. You can see our strong base and our strong acid will recombine to form an ionic compound and water. So since we know that sodium hydroxide is a strong base, the sodium hydroxide will completely dissociate in solution, as will our strong acid. In addition, sodium chloride is highly soluble and dissociates in water. And so if we eliminate here the spectator ions, I can see that Na plus does not participate in the reaction, and Cl minus does not participate in the reaction. And so that's how we come to the net ionic equation, where we have H plus and hydroxide ion produces water. So when we have strong acid and base neutralization reaction, the changes in the pH can be monitored by setting the reaction up as a titration and then using the pH meter to measure the pH throughout. So the equivalence point here represents the stoichiometric balance when the moles of acid are equal to the moles of the base. Only for strong acid, strong base titrations will the pH at the equivalence point be equal to 7. Only for strong acid, strong base. Reactions involving weak acids or weak bases will produce acidic or basic salts. So the pH will not be equal to 7 in those cases. So let's look at an example. I have 25 milliliter sample of hydroiodic acid, that's one of our strong acids, and it requires 46.23 milliliters of 0.203 molar NaOH solution to reach the equivalence point. We're going to calculate the concentration of the acid. So to begin, we have to calculate the number of moles of hydroxide ions that are added. So we know that sodium hydroxide, NaOH, is a strong base, and so will completely dissociate in water. So that tells us that every 1 mole of sodium hydroxide is going to produce 1 mole of hydroxide ions. So I can use this molarity as my molarity for the hydroxide. So the number of moles is going to be equal to the molarity times the volume. Remember, your volume has to be in liters for this calculation. So I'll have 0.203 molar times 0.04623 liters, and so I'll get 0.009385. And I know this is a couple extra digits because I only have 3 significant figures here, but I don't want to introduce any rounding error into my calculations that come later. So I'm just going to keep an extra digit here. So now I know the number of moles of my hydroxide ions, and using the stoichiometry of the balanced equation to convert to moles of HI, well, HI plus NaOH is going to yield NaI. There's that ionic compound plus H2O. And I've got 1H and 1H and 1OH and 1OH and 1I and 1I and 1 Na and 1 Na. So this is balanced. So for every 1 mole of NaOH, I also need 1 mole of hydroiodic acid. So I have a 1-to-1 ratio. So the number of moles I calculated here is equal to the number of moles of HI. So to get to the concentration, that's my molarity, I'm going to rearrange M is equal to N over V. And remember now, this V is the combined volume. So I've combined these solutions. So my number of moles, 0.009385, will be divided by the total volume, 0.0250 plus 0.04623. And so this comes out to 0.13 molar. And I know it has two significant digits. Actually, this has 3, so I'll be to the, this should be one more digit. Okay, moving on. The previous calculation was a lot easier due to the fact that everything ionizes 100%. There's a little more difficulty involved where we have one weak and one strong acid or base. So let's look at an example where we have a weak acid, like acetic acid, and a strong base, like sodium hydroxide. So sodium hydroxide, again, will completely dissociate in solution. My weak acid will not, so this stays as the molecular form. And here's my ionic compound, so I'll have, again, Na plus and my acetate ion. So I can see that the sodium is the spectator. And so this produces, this is a general form of the net ionic equation, but I have my hydroxide ion plus my weak acid, that's here, produces the negative ion from the acid and water. So just as before, the changes in pH can be monitored by setting up a titration and using a pH meter to track the pH. The equivalence point, again, is the stoichiometric balance, where the number of moles of my weak acid present at the start are equal to the number of moles of sodium hydroxide that are added. But remember that strong acid and strong base titrations will have a pH of 7 at the equivalence point. But when I have a weak acid or base, this equivalence point gets pulled off of neutral. And so because it will make a salt that is either acidic or basic. In this case, I have a strong base and a weak acid. So you can think of this like a game of tug of war. The strong base is going to pull harder, form a basic salt, and so that pH is going to be pulled up in the basic direction. So here's our next example. We're going to calculate the pH on the titration of 25 milliliters of 0.1 molar acetic acid by sodium hydroxide after the addition to the acid solution of 35 milliliters of 0.1 molar NaOH. And they give me my Ka value. So my first step, I'm going to calculate the number of moles of hydroxide ions added. So again, using N equals M times V. I have my molarity is, and I want hydroxide ions, so I'm looking for NaOH. Okay, so my molarity is 0.100 times my volume in liters, so 0.0350 liters. So that's going to come out to 0.00350 moles. Then I want to calculate the number of moles of my weak acid. So again, N is equal to M times V. So this will be equal to 0.100 molar times now 25 milliliters, remembering to convert to liters, and that'll be equal to 0.00250 moles. And so we can see that we have more moles of the hydroxide ions than we have moles of our weak acid. And so this means that we're going to use up all of our weak acid, and we'll use up an equivalent amount of hydroxide ions, but we'll have some left over. So to calculate how much I have left over or excess, I'm just going to simply subtract. So 0.00350 minus 0.00250 gives me an excess of 0.00100 moles of hydroxide ions. Next, I'm going to calculate the hydroxide ion concentration, remembering that I now have a combined solution, so I need to use the combined volume. So I want my concentration, that's the molarity, so I'm going to rearrange. M is equal to N over V. So my N was 0.00100 moles. And I'm dividing by my total volume. So I had 25 milliliters plus 35 milliliters is 60 milliliters. And then I have to convert to liters, so 0.0600 liters. And so this is going to come out to 0.0167, keeping an extra digit so that I don't end up with rounding error. This says to convert to the hydrogen ion concentration. I feel like for me, I prefer to go to POH and then pH because those equations are easier for my brain to remember. So I'm going to do my POH next. So POH is equal to the negative log of my hydroxide ion concentration. So that's the negative log of 0.0167, which comes out to 1.78. And then my pH is equal to 14 minus my POH. So 14 minus 1.78. So this comes out to 12.22. So now I have the pH of this solution. So the example we just completed had excess of the strong base. If the weak acid is in excess, then the resulting solution is called a buffer solution. A buffer solution contains relatively high concentrations of a conjugate acid and base pair. If a small amount of a strong acid or base is added to this buffer solution, then the buffer solution resists changes to the pH because it's neutralizing that acid or base as you add it. So the Henderson-Hasselbalch equation can be used to determine the pH of the resulting solution. Buffers and the Henderson-Hasselbalch equation will be discussed more later in the unit. Looking at the opposite situation now, weak base and strong acid is very similar. So if the weak base is in excess, it again will produce that buffer solution, and so we'll use the Henderson-Hasselbalch equation. But if the strong acid is in excess, then we do essentially the same analysis that we just did. The pH of the resulting solution will be calculated based on the molarity of the solution formed from the excess moles of the hydronium ion divided by the total volume. The last situation to consider is when things are equimolar, meaning the same number of moles of the weak base and the strong acid. This means that we're already at the equivalence point, and we'll learn to calculate for both of these situations later in this unit. The last possible situation is weak acid and weak base. So if a weak acid and a weak base are combined, the resulting solution will reach equilibrium, and the reaction can be shown as the weak acid plus the weak base produces the negative A ion plus the positive HB ion. So let's do the IDU. So our IDU example, I have 100 milliliters of 0.1 molar acetic acid, and it's added to 100 milliliters of 0.1 molar potassium hydroxide. I'm going to calculate the pH of the resulting solution, and my Ka value is given. So let's just do our overall overall equation first. So I have acetic acid plus potassium hydroxide produces potassium acetate and water. Potassium hydroxide, though, is a strong base, and so my strong base will completely dissociate, and my ionic compound, anything with potassium and acetate are both highly soluble, so this will also dissociate. And so I'm going to eliminate my spectator ions, the potassium and the potassium. My weak acids are not going to dissociate as much, and so my acetate ion is not a spectator. So my net ionic equation here will be the acetic acid plus the hydroxide ion produces acetate ion and water. Okay, analyzing my moles, I see that 0.1 molar at 100 milliliters comes out to 0.01 moles. And then I have the same situation for my potassium hydroxide. So this is equimolar. So I need to do an ICE analysis in order to find my concentration of hydroxide ions. So I'm going to rewrite down here, and I'm going to turn this around because when it's equimolar, this reaction is going to go to completion, and then the weak acid is going to reestablish equilibrium. So, plus I need to write the K value for this, and I can't do it with H2O over there. So my K value means that I have to flip this around. So I'll have my water plus my acetate produces acetic acid and hydroxide. Okay, so ICE, water doesn't matter. So my reaction went to completion. Remember, this was on the product side before. So when my reaction goes to completion, I had acetate ions were 0.1 molar, and then this is now the combined solution. So I have 200 milliliters of solution. So I doubled the volume, which means that my molarity will be halved. So 0.0500 is my new molarity. And I said again, this goes to completion, so I'll have 0 of these. And so minus X and plus X and plus X. So I'll have 0.0500 minus X, X, and X. And since I have hydroxide here, this will be my Kb expression. So Kb is equal to the concentration of the acetic acid, times the concentration concentration of the hydroxide, all over concentration of acetate. So my Kb is equal to x times x, so x squared, all over 0.05 minus x. But they gave me Ka. So I actually need to calculate my Kb in order to solve this. So Kw is equal to Ka times Kb. So rearranging, Kb is equal to Kw divided by Ka. Well, remember that Kw is equal to 1 times 10 to the negative 14 divided by the Ka that's given, 1.8 times 10 to the negative 5th. So my Kb is going to be equal to 5.6 times 10 to the negative 10. So I'm going to substitute that into my expression for Kb. Okay, and then 10 to the minus 10 is very small, much smaller than 1 times 10 to the negative 4. So I can ignore that x in the denominator when I'm solving. So x is equal to 5.3 times 10 to the negative 6 molar. And remember, x is also the concentration of the hydroxide ion. Okay, so I'm trying to find the pH. I now have the concentration of the hydroxide ion. I can calculate my pOH. So that's equal to the negative log of the concentration of hydroxide, which was 5.3 times 10 to the minus 6. So my pOH is going to be equal to 5.28. And then pH is equal to 14 minus my pOH, 5.28. So my pH is going to be equal to 8.72. Okay? Let's try the we do. So they want to know what's the pH of a solution composed of 500 milliliters of 0.25 molar sodium hydroxide. That's a strong base. And 400 milliliters of 0.2 molar hydrochloric acid. That's a strong acid. Okay, so when I have a strong acid and a strong base, I need to do the mole calculations first. So N is equal to M times B. I'm going to do my NaOH over here. So my molarity was 0.250. My volume in liters is 0.5000 liters. So this comes out to 0.125 moles. Looking at hydrochloric acid, I have 0.200 molar times 0.4 liters. So my moles will be 0.0800 moles. And so we can see 0.125 is greater than 0.08. And so I'm going to calculate my excess NaOH. So 0.125 minus 0.0800 gives me 0.0450. Oop, not that last one. Moles of excess hydroxide. So now I need to calculate the concentration of the hydroxide. So the concentration will be M is equal to N over V. And remember, this is now the combined volume. So 0.045 all over. I had 500 milliliters plus 400 milliliters. So that's going to be a total of 900 milliliters. And this comes out to 0.050 molar hydroxide ions. So I can calculate my POH. POH is equal to the negative log of my hydroxide ion concentration, which is 0.050. So my POH is 1.30. And then my pH is equal to 14 minus my POH. And my POH was 1.3. So 14 minus 1.3 is 12.70. That's it for these notes. Good luck on your homework.